To derive the formula for resistors in series and parallel. So this is a resistor in series, meaning it is connected end to end, it is joined end to end. So that's for series, straight line. Then like series horizontally. Then for resistors in parallel, we have here they are connected from like side by side, so from one point to this other point. So one thing you should notice is that in resistors in series we have the same current I flowing through it, the same current but different voltage. So different voltage. This voltage here is going to be different from the one here, going to be different from the one here. So in this case here we have we can now say using Ohm's law V is equal to IR. So in this case here you can see that the total voltage here is going to be the total voltage passing through the circuit is going to be total voltage V equal to V1 plus V2 plus V3, right? So in this case here, if you check V1, if you want to get the voltage for V1 will be R1, the resistor one here, times this the current. Since it's the same current, V2 will be IR2. So let's try that out. So here V1 equals to IR1, V2 equals to IR2, and V3 equals to IR3. So the same current. So we can now substitute this value into this place. We are going to have, remember, V is equals to IR. So substituting this value, we have V is IR. So substitute here, IR is equal to V1 is what? IR1 plus V2 is IR2 plus V3 is IR3. Okay, bring out the common factor. IR is equal to IR1 plus R2 plus R3. In this case, this I is going to cancel this I, so therefore we have the total resistor in a series connection is going to be R1 plus R2 plus R3. That's for the one in series. So you can try to derive this yourself. In deriving it, it makes it very difficult for you to forget the formula when solving. Most persons interchange it so that you can understand the concept. So we'll come back to the one in parallel. It has from this point to this point, it has the same voltage. We're going to have the same voltage here and then different current. So the same voltage, different current. So the first resistor is going to have first current I1 is going to be I2, I3. So if we're going to apply the same Ohm's law here, apply the same Ohm's law, so the total current I will be I1 plus I2 plus I3. So for this first one, the same volt. So the first one here, so let's say V is equals to IR. So I1 will be equal to V over R1. That's for I1. I2 will be equal to V over R2. Then I3 will be V over R3. The same volt, making I substitute the formula from here. we can put this value here. So I is V over R. So we have V over R. We have V over R is equal to I1 is V over R1 plus I2 is V over R2 plus V over R3, right? So we can bring out the common factor here. We have V over R is equal to V 1 over R1 plus 1 over R2 plus 1 over R3. So we bring out the common factor. So this V can cancel this V. We cancel this out. So we have 1 over R is equal to, the total resistor is 1 over R1 plus 1 over R2 plus 1 over R3. So that's how to derive. So that's the formula for resistor in series is R1 plus R2 plus R3, right? The one in parallel is the inverse of this. So in the next video we're going to derive for capacitors. So try to derive this yourself so that you understand. Note, in series connection we have the same current flowing through all the individual resistors, different voltage, while in parallel we have the same voltage, different current.